Md5.
The Md5 message digest algorithm is a widely used cryptographic hash function producing a 128-bit hash value, typically expressed in text format as a 32-digit hexadecimal number. Md5 has been utilized in a wide variety of cryptographic applications, and is also commonly used to verify data integrity. Md5 was designed by Ron Rivest in 1991 to replace an earlier hash function, Md4. The source code in RFC 1321 contains a by attribution RSA license. In 1996 a flaw was found in the design of Md5. While it was not deemed a fatal weakness at the time, cryptographers began recommending the use of other algorithms, such as SHA-1, which has since been found to be vulnerable as well. In 2004 it was shown that Md5 is not collision resistant. As such, Md5 is not suitable for applications like SSL certificates or digital signatures that rely on this property for digital security. Also in 2004 more serious flaws were discovered in Md5, making further use of the algorithm for security purposes questionable. Specifically, a group of researchers described how to create a pair of files that share the same Md5 checksum. Further advances were made in breaking Md5 in 2005, 2006, and 2007. In December 2008, a group of researchers used this technique to fake SSL certificate validity, and CMU Software Engineering Institute now says that Md5 should be considered cryptographically broken and unsuitable for further use, and most U.S. government applications now require the SHA-2 family of hash functions. In 2012, the flame malware exploited the weaknesses in Md5 to fake a Microsoft digital signature.
History and cryptanalysis.
Md5 is one in a series of message digest algorithms designed by Professor Ronald Rivest of MIT, Rivest, 1992. When analytic work indicated that Md5's predecessor Md4 was likely to be insecure, Md5 was designed in 1991 to be a secure replacement. Weaknesses were indeed later found in Md4 by Hans Dobbertin. In 1993, Denboer and Bosseliers gave an early, although limited, result of finding a pseudo-collision of the Md5 compression function. That is, two different initialization vectors which produce an identical digest. In 1996, Dobbertin announced a collision of the compression function of Md5, Dobbertin, 1996. While this was not an attack on the full Md5 hash function, it was close enough for cryptographers to recommend switching to a replacement, such as SHA-1 or RIPEND 160. The size of the hash value, 128 bits, is small enough to contemplate a birthday attack. Md5 CRK was a distributed project started in March 2004 with the aim of demonstrating that Md5 is practically insecure by finding a collision using a birthday attack. Md5 CRK ended shortly after August 17, 2004, when collisions for the full Md5 were announced by Xiaoran Wang, Dengguo Feng, Zhu Li, and Hongbo Yu. Their analytical attack was reported to take only 1 hour on an IBM P690 cluster. On March 1, 2005, Arjun Lenstra, Xiaoran Wang, and Ben de Weger demonstrated construction of two X509 certificates with different public keys and the same Md5 hash value, a demonstrably practical collision. The construction included private keys for both public keys. A few days later, Vlastimil Klima described an improved algorithm, able to construct Md5 collisions in a few hours on a single notebook computer. On March 18, 2006, Klima published an algorithm that can find a collision within 1 minute on a single notebook computer, using a method he calls tunneling. Various Md5-related RFC errata have been published. In 2009, the United States Cyber Command used an Md5 hash value of their mission statement as a part of their official emblem. On December 24, 2010, Tao Xi and Dengguo Feng announced the first published single-block, 512-bit, Md5 collision. Previous collision discoveries relied on multi-block attacks. For security reasons, Xianfeng did not disclose the new attack method. They have issued a challenge to the cryptographic community, offering a $10,000 reward to the first finder of a different 64-byte collision before January 1, 2013. Mark Stevens responded to the challenge and published colliding single-block messages as well as the construction algorithm and sources. In 2011, an informational RFC 6151 was approved to update the security considerations in Md5 and HMAC Md5.
Security.
The security of the Md5 hash function is severely compromised. A collision attack exists that can find collisions within seconds on a computer with a 2.6 GHz Pentium 4 processor, complexity of 224.1. Further, there is also a chosen prefix collision attack that can produce a collision for two inputs with specified prefixes within hours, using off-the-shelf computing hardware, complexity 239. The ability to find collisions has been greatly aided by the use of off-the-shelf GPUs. On an NVIDIA GeForce 8400GS graphics processor, 16 to 18 million hashes per second can be computed. An NVIDIA GeForce 8800 Ultra can calculate more than 200 million hashes per second. These hash and collision attacks have been demonstrated in the public in various situations, including colliding document files and digital certificates.
Collision vulnerabilities.
In 1996, collisions were found in the compression function of Md5, and Hans Dobbertin wrote in the RSA Laboratories technical newsletter, "The presented attack does not yet threaten practical applications of Md5, but it comes rather close. In the future Md5 should no longer be implemented where a collision-resistant hash function is required." In 2005, researchers were able to create pairs of PostScript documents and X509 certificates with the same hash. Later that year, Md5's designer Ron Rivest wrote, "Md5 and SHA-1 are both clearly broken, in terms of collision resistance." On December 30, 2008, a group of researchers announced at the 25th Chaos Communication Congress how they had used Md5 collisions to create an intermediate certificate authority certificate which appeared to be legitimate when checked via its Md5 hash. The researchers used a cluster of Sony PlayStation 3 units at the EPFL in Lausanne, Switzerland to change a normal SSL certificate issued by Rapid SSL into a working CA certificate for that issuer, which could then be used to create other certificates that would appear to be legitimate and issued by Rapid SSL. VeriSign, the issuers of Rapid SSL certificates, said they stopped issuing new certificates using Md5 as their checksum algorithm for Rapid SSL once the vulnerability was announced. Although VeriSign declined to revoke existing certificates signed using Md5, their response was considered adequate by the authors of the exploit, Alexander Sotorov, Mark Stevens, Jacob Appelbaum, Arjen Lenstra, David Molnar, Dag Arnosvik, and Ben de Weger. Bruce Schneier wrote of the attack that he already knew that Md5 is a broken hash function, and that no one should be using Md5 anymore. The SSL researchers wrote, "Our desired impact is that certification authorities will stop using Md5 in issuing new certificates. We also hope that use of Md5 in other applications will be reconsidered as well." In 2012, according to Microsoft, the authors of the Flame malware used an Md5 collision to forge a Windows code signing certificate. Md5 uses the Merkle-Damgard construction, so if two prefixes with the same hash can be constructed, a common suffix can be added to both to make the collision more likely to be accepted as valid data by the application using it. Furthermore, current collision finding techniques allow to specify an arbitrary prefix. An attacker can create two colliding files that both begin with the same content. All the attacker needs to generate two colliding files is a template file with a 128-byte block of data, aligned on a 64-byte boundary that can be changed freely by the collision finding algorithm. An example Md5 collision, with the two messages differing in 6 bits, is Both produce the Md5 hash 79,054,025,255 FB1A26E4BC422E54EB4. The difference between the two samples is the leading bit in each nibble has been flipped. For example, the 20th byte, offset 0x13, in the top sample, 0x87, is 10,111 in binary. The leading bit in the byte, also the leading bit in the first nibble, is flipped to make 0000111, which is 0x07 as shown in the lower sample. Later it was also found to be possible to construct collisions between two files with separately chosen prefixes. This technique was used in the creation of the Rogue CA certificate in 2008.
Primates Vulnerability.
In April 2009, a primage attack against Md5 was published that breaks Md5's primage resistance. This attack is only theoretical, with a computational complexity of 2123.4 for full primage.
Other vulnerabilities.
A number of projects have published Md5 rainbow tables online, which can be used to reverse many Md5 hashes into strings that collide with the original input, usually for the purposes of password cracking. The use of Md5 in some websites' URLs means that search engines such as Google can also sometimes function as a limited tool for reverse lookup of Md5 hashes. Both these techniques are rendered ineffective by the use of a sufficiently long salt.
Applications.
Md5 digests have been widely used in the software world to provide some assurance that a transferred file has arrived intact. For example, file servers often provide a pre-computed Md5, known as Md5 sum, checksum for the files, so that a user can compare the checksum of the downloaded file to it. Most Unix-based operating systems include Md5 sum utilities in their distribution packages. Windows users may install a Microsoft utility, or use third-party applications. Android ROMs also utilize this type of checksum. However, now that it is easy to generate Md5 collisions, it is possible for the person who created the file to create a second file with the same checksum, so this technique cannot protect against some forms of malicious tampering. Also, in some cases, the checksum cannot be trusted, for example, if it was obtained over the same channel as the downloaded file, in which case Md5 can only provide error-checking functionality. It will recognize a corrupt or incomplete download, which becomes more likely when downloading larger files. Md5 can be used to store a one-way hash of a password, often with key stretching. Along with other hash functions, it is also used in the field of electronic discovery, in order to provide a unique identifier for each document that is exchanged during the legal discovery process. This method can be used to replace the bait stamp numbering system that has been used for decades during the exchange of paper documents.
Algorithm.
Md5 processes a variable length message into a fixed length output of 128 bits. The input message is broken up into chunks of 512-bit blocks, 1632-bit words. The message is padded so that its length is divisible by 512. The padding works as follows. First, a single bit, 1, is appended to the end of the message. This is followed by as many zeros as are required to bring the length of the message up to 64 bits fewer than a multiple of 512. The remaining bits are filled up with 64 bits representing the length of the original message, modulo 264. The main Md5 algorithm operates on a 128-bit state, divided into 4 32-bit words, denoted A, B, C and D. These are initialized to certain fixed constants. The main algorithm then uses each 512-bit message block in turn to modify the state. The processing of a message block consists of 4 similar stages, termed rounds. Each round is composed of 16 similar operations based on a nonlinear function f, modular addition, and left rotation. Figure 1 illustrates one operation within a round. There are 4 possible functions f. A different one is used in each round. Denote the XOR, and OR are not operations respectively.
Sudi Code.
The Md5 hash is calculated according to this algorithm. All values are in little endian. Note: instead of the formulation from the original RFC 1321 shown, the following may be used for improved efficiency, useful if assembly language is being used, otherwise, the compiler will generally optimize the above code. Since each computation is dependent on another in these formulations, this is often slower than the above method where the NAND can be parallelized.
Md5 Hashes.
The 128-bit, 16-byte, Md5 hashes, also termed message digests, are typically represented as a sequence of 32 hexadecimal digits. The following demonstrates a 43-byte ASCII input and the corresponding Md5 hash. Even a small change in the message will, with overwhelming probability, result in a mostly different hash, due to the avalanche effect. For example, adding a period to the end of the sentence. The hash of the zero-length string is. The Md5 algorithm is specified for messages consisting of any number of bits. It is not limited to multiples of 8-bit, octets, bytes, as shown in the examples above. Some Md5 implementations such as Md5 Sum might be limited to octets, or they might not support streaming for messages of an initially undetermined length.
Simple implementation.
A simple Md5 implementation in C++ that follows the pseudocode. The message to hash is passed via the first argument of the command line.